In this video, we learn how to determine the rate law of a chemical reaction using the differential or Van Hoff method. Right, so the idea is as follows. Suppose that we have a chemical reaction with only one reagent, A to the phi, and that means that we can determine, or we can write the rate law right away. Rate is going to be equal to minus the change in concentration of A, differential of time, and then K, concentration of A to the X. Okay, so again, we're trying to determine here what the rate law is, so that means that we have to determine what the rate constant is and what the reaction order with respect to A is. So we have seen two methods until now. One of them is the integration method, in which you just measure the concentration of A as a function of time and try to use the integrator laws to see what fits the variation of the concentration of A as a function of time best. We've also seen the half-life method. Now, those methods have the inconvenience that they might not work if you have non-integer reaction orders like 1.5 or 1.25 or any such non-integer reaction order. This method, the Van Hoff method, is the most universal one because it has no restrictions on what type of reaction orders you can access. Right, so the idea here is as follows. You can rewrite this rate law simply as V is equal to K concentration of A to the X. Okay, and the idea here is that if you take the base 10 logarithms of this expression, okay, you get to an expression that is like this. The logarithm of the rate is equal to the logarithm of all of this, K concentration of A to the X. Okay. Now, what you can actually do is use the properties of the logarithms to replace that product by the sum of the logarithms. Okay, so you'll have that this is equal to the logarithm of the rate constant plus the logarithm of the concentration of A as a function up to the power of X, the reaction order. And then you can further use the property of the logarithms to take that exponent out as a factor. Okay, so right away you actually find that you obtain a linear expression which looks like this. Notice that this is y is equal to a plus mx. Alright, so if you're able to measure the rate at various concentrations of A, then you can actually be able to plot the base 10 logarithm of the rate as a function of the base 10 logarithm of the concentration of A, and then that should give you a straight line. The intercept with the y-axis would be the base 10 logarithm of the rate constant, and the slope is directly the reaction order. Okay, so let's actually draw here a linear representation, or let's actually draw how that would look like. So again, what would you plot here? You would plot here is the base 10 logarithm of the rate versus the base 10 logarithm of the concentration of A. And again, notice that according to this derivation that we just have carried out, okay, what you would find is that this should be the equation of a straight line. Okay, and again, what you're plotting here, again, you will be measuring the rate as a function of the concentration of reagent, and then taking the base 10 logarithm of each and plotting them like this. Okay, so suppose that you get that should be a straight line. Okay, and then the slope is directly the reaction order that you're looking for. And also interestingly, that intercept is the base 10 logarithm of the rate constant. Okay, so for a few measurements of the rate for various concentrations of a reagent, then you can obtain the entire rate law, both the rate constant and also the reaction order. Notice that in this method there's no restriction as to what the order can be. This x can be 1.5, 1.7, it can be non-integer or integer, and you also can get the rate constant rather nicely. Okay. Now, something that is interesting about this method is that usually we typically employ this method with something that is called the initial rates. Okay, so all of these will have a sub-zero, and you will see this in problems. Okay, meaning that you're measuring the rate at the start of the reaction. Okay, rate at time 0, concentration times 0, rate at times concentration at time 0, rate at time 0. Okay, and there's various reasons to actually try to measure that are advantageous, or there's a couple of reasons why measuring the initial rate or carrying out this method with initial rate is advantageous over taking the rate at any other time. Okay, so notice that what we're doing here is trying to calculate the rate at the start of the reaction. So if we plot the concentration of A as a function of time, and this can have any dependence, okay, we're trying to determine that. The idea would be that we're trying to measure the slope of the line tangent to this curve at very early reaction times. And again, there's a couple of reasons for that. For one, usually you can determine concentrations very easily when the concentration is high. Okay, so you have much more accuracy at the start of the reaction where the concentration of reagents is high. Now, if you actually go to very long times where the reaction might be, where the concentration of reagent might be very small, then determining the concentration might be actually not so easy. Okay. Now, another more important reason is that as the reaction proceeds, well, when at the start of the reaction, you actually have very little product available, and sometimes what happens is that products interfere with the determination of A. So suppose that you're trying to determine the concentration of your reagent using UV spectroscopy. If this is at the start of the reaction, then the amount of P that is going to be interfering with the signal that you get for A will be very minor, and you can completely neglect it. However, if you go and try to determine the concentration of A after some time has elapsed, then you're going to have quite a bit of product around, and that product might interfere, might overlap with the spectrum for your reagent, and then decoupling the signal for the product and the reagent will be difficult. Okay, so again, it's pretty common to use initial rates. They are advantageous. They are much easier to determine than the rate at any time. And again, in essence, this is what the differential or Van Hoff method is for a reaction that only has one reagent. In the following, we're actually going to try to determine how to use the Van Hoff method when you actually have two reagents.